NFPA 70, the National Electrical Code, Section 517.40 does not specifically require galvanized steel conduit for emergency power systems in skilled nursing facilities. NFPA 110, Standard for Emergency and Standby Power Systems, Section 11.12.1 requires raceways and fittings for emergency power systems to be of material suitable for the location and installed in accordance with the applicable requirements of NFPA 70. NFPA 70, Article 358 pertains to metallic raceway systems. Section 358.10 states that raceways shall be installed in compliance with the provisions of this article and the requirements governing the particular type of raceway installed. Based on the above code sections, there is no specific requirement in NFPA 70 or NFPA 110 that mandates galvanized steel conduit for emergency power and skilled nursing facilities. However, Section 358.10 of NFPA 70 requires raceways to be installed in accordance with the requirements governing the particular type of raceway installed. Some jurisdictions may have additional local codes or requirements that could specify the use of galvanized steel conduit for emergency power systems and skilled nursing facilities. It is always advisable to check with the local authority having jurisdiction to determine if any such requirements exist. In the absence of any specific code requirement or local regulations, the use of galvanized steel conduit for the emergency power system in the skilled nursing facility is not mandatory. However, it is important to ensure that the conduit material selected is suitable for the location and meets the requirements of NFPA 70, Article 358. When deciding on the type of conduit for electrical installations, especially in critical systems like emergency power, several factors beyond the National Electrical Code and NFPA standards need careful consideration. These factors often involve the specific environment, the type of building, and the potential for corrosion or physical damage. Understanding these aspects can lead to a more robust and reliable installation. Firstly, consider the environment. The location of the conduit, whether it's indoors or outdoors, significantly impacts the choice of material. Outdoor installations are exposed to weather elements such as rain, snow, and sunlight, which can degrade certain materials over time. In coastal areas, the presence of salt in the air can accelerate corrosion, making galvanized steel or even more corrosion-resistant materials like stainless steel a necessity. Secondly, assess the potential for physical damage. In areas where the conduit is likely to be exposed to mechanical stress such as vehicular traffic or heavy equipment, rigid metal conduit, or RMC, offers superior protection compared to thinner-walled options like electrical metallic tubing, or IMT. The thicker walls of RMC can withstand significant impacts, safeguarding the conductors within. Thirdly, consider the type of building. Skilled nursing facilities, due to their function, often have specific requirements related to fire safety and patient well-being. While the NEC and NFPA 110 provide general guidelines, local building codes may impose stricter standards for materials used in these facilities. For instance, some jurisdictions might require the use of metal conduit for all electrical wiring to minimize the risk of fire spread and to provide better electromagnetic shielding. Fourthly, investigate local amendments. Local authorities often amend the national codes to address specific concerns within their jurisdiction. These amendments can be more stringent than the national codes and may mandate the use of galvanized steel conduit in certain applications. Always check with the local authority having jurisdiction to determine if any such amendments exist. Fifthly, review project specifications. In many construction projects, particularly those involving government or institutional clients, the project specifications may include requirements that go beyond the minimum code standards. Architects and engineers often specify materials and installation methods that provide an extra margin of safety and reliability. These specifications may call for galvanized steel conduit even if it's not explicitly required by the NEC or NFPA standards. Sixthly, consider the life cycle cost. While galvanized steel conduit may have a higher initial cost compared to other options like PVC conduit, it often has a longer lifespan and requires less maintenance. Over the long term, the total cost of ownership may be lower for galvanized steel conduit, especially in harsh environments where other materials would need to be replaced more frequently. Seventhly, evaluate grounding requirements. Metal conduit systems provide an effective grounding path for electrical circuits, which is essential for safety. Galvanized steel conduit, when properly installed and bonded, can help to minimize the risk of electrical shock and equipment damage in the event of a fault. Eighthly, check for industry best practices. While not legally binding, industry best practices often reflect the collective experience and knowledge of electrical professionals. These practices may recommend the use of galvanized steel conduit in certain applications based on its proven performance and reliability. Ninthly, consider future expansion. When designing an electrical system, it's important to anticipate future needs and plan for potential expansion. Using a robust conduit system like galvanized steel can make it easier to add new circuits and equipment in the future without having to replace the entire conduit system. Tenthly, consult with experienced professionals. Electrical contractors, engineers, and inspectors can provide valuable insights and recommendations based on their experience with similar projects. Their expertise can help ensure that the conduit system is properly designed and installed to meet the specific needs of the facility. In summary, while the NEC and NFPA 110 may not explicitly require galvanized steel conduit for emergency power systems and skilled nursing facilities, various factors can influence the choice of conduit material. Local codes, project specifications, environmental conditions, and industry best practices should all be considered to ensure a safe, reliable, and cost-effective installation. By taking a comprehensive approach to conduit selection, electrical contractors can help to protect the health and safety of patients and staff in skilled nursing facilities. Furthermore, it is essential to understand the different types of conduit available and their specific applications. Firstly, rigid metal conduit, or RMC, is a heavy-duty option often made of galvanized steel. It provides excellent protection against physical damage and is suitable for both indoor and outdoor use. RMC is typically used in areas where the conduit is exposed to significant mechanical stress or corrosive environments. Secondly, intermediate metal conduit, or IMC, is a lighter weight version of RMC. It offers similar protection but is easier to work with and less expensive. IMC is commonly used in commercial and industrial applications where a high level of protection is required. Thirdly, electrical metallic tubing, or EMT, is a thin-walled conduit made of galvanized steel or aluminum. It is lighter and easier to bend than RMC or IMC, making it a popular choice for indoor applications. EMT is typically used in residential and commercial buildings for branch circuits and feeders. Fourthly, flexible metal conduit, or FMC, is a spiral wound conduit that can be bent easily. It is used to connect electrical boxes and equipment in tight spaces or where vibration is a concern. FMC is not suitable for wet locations unless it is specifically listed for that purpose. Fifthly, liquid-type flexible metal conduit, or LFMC, is a flexible metal conduit that is covered with a waterproof plastic coating. It is used in wet or damp locations to protect conductors from moisture and corrosion. LFMC is commonly used for outdoor lighting, HVAC equipment, and other applications where exposure to water is a concern. Sixthly, rigid polyvinyl chloride conduit, or PVC, is a non-metallic conduit made of rigid plastic. It is lightweight, corrosion-resistant, and easy to install. PVC conduit is commonly used in underground applications and in areas where exposure to chemicals is a concern. Seventhly, electrical non-metallic tubing, or ENT, is a flexible non-metallic conduit that is similar to FMC. It is lightweight and easy to bend, making it a popular choice for residential and light commercial applications. ENT is typically used for concealed wiring in walls and ceilings. When selecting conduit, it is important to consider the following factors. Firstly, the type of environment. Is the conduit exposed to moisture, chemicals, or physical damage? Secondly, the type of wiring. What type of conductors will be installed in the conduit? Thirdly, the applicable codes and standards. Does the NEC or local building code specify the type of conduit that must be used? Fourthly, the cost. What is the total cost of the conduit, including materials and labor? By carefully considering these factors, electrical contractors can ensure that the conduit system is properly designed and installed to meet the specific needs of the facility. In the specific case of a 75 kilowatt generator installation in a skilled nursing facility in California, several additional considerations come into play. Firstly, California Electrical Code, or SEC. California adopts the NEC with some state-specific amendments. It's crucial to verify if California has any specific requirements regarding conduit types for emergency power systems and healthcare facilities. Secondly, seismic considerations. California is prone to earthquakes, so the installation must comply with seismic requirements. The conduit system should be able to withstand seismic activity without compromising the integrity of the electrical system. This might influence the choice of supports and the type of conduit used. Thirdly, OSHP requirements. Projects involving healthcare facilities in California often fall under the jurisdiction of the Office of Statewide Health Planning and Development, or OSHP. OSHP has its own set of requirements that may be more stringent than the NEC or CC. Check with OSHP to determine if there are any specific requirements for conduit types in emergency power systems. Fourthly, generator location. The location of the generator, whether it's indoors or outdoors, will affect the choice of conduit material. Outdoor installations require conduit that is resistant to weather and corrosion. Fifthly, fuel type. The type of fuel used by the generator, whether it's diesel, natural gas, or propane, may affect the choice of conduit material. Some fuels are more corrosive than others and may require the use of corrosion-resistant conduit. Sixthly, coordination with other trades. Coordinate with other trades, such as mechanical and plumbing, to ensure that the conduit system does not interfere with their work. Proper coordination can help to avoid costly rework and delays. Seventhly, documentation. Maintain thorough documentation of the conduit installation, including drawings, specifications, and inspection reports. This documentation will be helpful for future maintenance and troubleshooting. Eighthly, training. Ensure that all personnel involved in the installation are properly trained and qualified. Proper training can help to prevent errors and ensure that the installation is done safely and correctly. Ninthly, inspection. Have the conduit installation inspected by a qualified inspector to ensure that it complies with all applicable codes and standards. A thorough inspection can help to identify any potential problems before they become serious. Tenthly, maintenance. Develop a maintenance plan for the conduit system to ensure that it remains in good condition over time. Regular maintenance can help to prevent corrosion, damage, and other problems that could compromise the integrity of the electrical system. In conclusion, while the NEC and NFPA 110 may not explicitly require galvanized steel conduit for emergency power systems in skilled nursing facilities in California, various factors can influence the choice of conduit material. These factors include state and local codes, seismic considerations, OSHP requirements, generator location, fuel type, coordination with other trades, documentation, training, inspection, and maintenance. By carefully considering these factors, electrical contractors can ensure that the conduit system is properly designed and installed to meet the specific needs of the facility and to comply with all applicable codes and standards. It's also important to understand the specific installation requirements for galvanized steel conduit. Firstly, cutting. When cutting galvanized steel conduit, use a hacksaw or pipe cutter designed for metal. Avoid using torches or other methods that could damage the galvanizing coating. Secondly, threading. When threading galvanized steel conduit, use a threading machine or hand tools designed for metal. Apply cutting oil to the threads to prevent damage and ensure a tight fit. Thirdly, reaming. After cutting and threading galvanized steel conduit, ream the inside of the conduit to remove any burrs or sharp edges. This will prevent damage to the conductors when they are pulled through the conduit. Fourthly, joining. When joining sections of galvanized steel conduit, use threaded couplings or compression fittings designed for metal. Ensure that the couplings and fittings are properly tightened to provide a secure connection. Fifthly, supporting. Support galvanized steel conduit at intervals specified by the NEC. Use conduit hangers, straps, or clamps designed for metal. Ensure that the supports are securely fastened to the building structure. Sixthly, grounding. Ground galvanized steel conduit in accordance with the NEC. Use grounding bushings, lockuts, or clamps designed for metal. Ensure that the grounding connections are clean and tight. Seventhly, corrosion protection. In corrosive environments, apply a corrosion-resistant coating to galvanized steel conduit after installation. This will help to protect the conduit from rust and other forms of corrosion. Eighthly, expansion fittings. In long runs of galvanized steel conduit, use expansion fittings to allow for thermal expansion and contraction. This will prevent the conduit from buckling or pulling apart. Ninthly, sealing. Seal the ends of galvanized steel conduit to prevent moisture and debris from entering the conduit. Use conduit sealant or duct seal designed for metal. Tenthly, inspection. Inspect the galvanized steel conduit installation after completion to ensure that it complies with all applicable codes and standards. Correct any deficiencies promptly. Furthermore, understanding the NEC Article 358 on electrical metallic tubing is critical. 358.1 discusses the scope of EMT. This article covers the use, installation, and construction specifications for electrical metallic tubing, or EMT, and associated fittings. 358.2 defines what EMT is. EMT is an unthreaded, thin-walled raceway of circular cross-section designed for the physical protection and routing of conductors and cables and for use as an equipment grounding conductor when installed utilizing appropriate fittings. 358.10 covers uses permitted. EMT and associated fittings are permitted for both exposed and concealed work. It is permitted in direct burial applications where protected by corrosion protection and identified for the use. It is permitted in concrete. It is permitted in wet, dry, and damp locations. 358.12 covers uses not permitted. EMT cannot be used where, during installation or afterward, it will be subject to severe physical damage. It cannot be used where protected from corrosion solely by enamel. It cannot be used in cinder concrete or cinder fill where subject to permanent moisture unless protected on all sides by a layer of non-cinder concrete at least 50 mm or 2 inches thick, or unless the tubing is at least 450 mm or 18 inches under the fill. It cannot be used in subject to severe corrosive influences. 358.20 covers size. The size of EMT is designated by its trade size, which does not correspond to the actual outside diameter of the tubing. EMT is available in trade sizes ranging from 1/2 inch to 4 inches. 358.22 covers number of conductors. The number of conductors permitted in EMT is governed by the percentage fill requirement specified in Chapter 9, Table 1 of the NEC. These requirements limit the cross-sectional area of conductors to a percentage of the cross-sectional area of the raceway. 358.24 covers bends. How made. Bends in EMT must be made so that the tubing is not damaged and the internal diameter of the tubing is not effectively reduced. The radius of the curve of the inner edge of any field bend must not be less than shown in Chapter 9, Table 2 of the NEC. 358.26 covers bends. Number in one run. There cannot be more than the equivalent of 4/4 bends, or 360 degrees total, between pull points, for example, conduit bodies and boxes. 358.28 covers supports. EMT must be securely fastened in place at intervals not exceeding 3 meters, or 10 feet. Additional supports may be required near boxes, cabinets, and fittings to ensure secure and stable installation. 358.30 covers securing and fastening. EMT must be securely fastened to boxes, cabinets, and fittings. Fittings used to connect EMT to boxes and cabinets must be designed and installed to ensure a reliable electrical connection and to prevent the tubing from pulling out. 358.42 covers couplings and connectors. Couplings and connectors used to connect lengths of EMT must be made up tight. Where buried in masonry or concrete, they must be listed and identified for the purpose. 358.56 covers splices and taps. Splices and taps are not permitted within ENT unless they are made in a box or conduit body that is accessible. These boxes and conduit bodies must be listed for the purpose and must provide adequate space for the splices and taps. These requirements ensure that ENT is installed in a manner that provides physical protection for conductors, maintains electrical continuity, and allows for future access and maintenance. Failure to comply with these requirements can result in unsafe installations, code violations, and potential hazards.